Welcome to today's Danfoss webinar, Determining if the Metering Device is Working Correctly, hosted by Jamie Kitchen. My name is Michael Beckerman, and I will be your moderator. During this 60-minute session, Jamie will show you how you can minimize unnecessary thermostatic expansion valve replacements and adjustments by identifying whether your metering device is injecting refrigerant correctly. Webinar attendees are muted, but I encourage you to submit your questions into the chat box found in the GoToWebinar module. We will answer a select number of your submissions at the conclusion of this session. Lastly, this webinar will be recorded and is available and will be available on demand at a later date. Subscribe to the Danfoss YouTube channel, Danfoss-KOOL US, to view that recording. Well, let's get started. I'm pleased to introduce the presenter for today's webinar, Jamie Kitchen, Danfoss Engineer. Jamie has over 30 years of experience with mechanical systems, 20 of which have been with Danfoss in the HVAC industry. Jamie, take it away.
Thank you, Michael. All right, as Michael mentioned, the focus today is going to be on, well, thermal expansion valves will take up a big part of it, but we really have to look at different types, whether it's simple restrictions or electronic expansion valves or whatever they happen to fall under. There's a couple things we need to do. Number one, we have to understand how they work. What causes them to function as they intended to? In other words, if you have a simple restriction, what causes the change in flow? If you have a TXV, what allows it to determine how much refrigerant it needs to inject into the metering device? We're also going to look beyond the metering device itself and look at key things that can happen in the system that are going to cause problems on the evaporator side, most of which really don't have anything to do with the TXV or with your metering device. They may end up looking like it does, but in fact, it is entirely something different. So there's two things. Number one, you have to understand or look at how something should be working under a given set of conditions so you can tell if it is or not. So let's start with the basics. What is the purpose of an expansion valve? Well, twofold. One, it helps to maintain the pressure difference in the system between the high and low side. Any AC or refrigeration system is really a heat pump. It pumps heat from one place where you don't want it to another place where you can either use it or you don't care. So if it's going to reject heat, it needs to have a high pressure, high temperature area. And if it's going to absorb heat, it needs a low pressure, low temperature area. And this is really what the expansion valve allows. The second thing is it has to inject refrigerant into the evaporator at a saturated state to replace what is boiling off into a vapor and being sucked in by the compressor. Otherwise, your evaporator would run out of liquid and things wouldn't work that great. So where does or what does the expansion part mean? Well, when you go through a metering device, you're either going through a small opening or down a narrow tube, and you have high pressure, confined spaces, friction losses, etc. When you leave that confined space, you suddenly increase in volume. And since you are expanding, a given mass of refrigerant taking up more volume is going to undergo a pressure drop. And this is key to how a metering device maintains a low temperature in the evaporator. Why? Well, the refrigerant is saturated. If it's saturated, vapor, liquid, you have that pressure temperature relationship. So you have liquid leaving, some vapor leaving, you have a pressure drop, you therefore have a temperature drop. But remember, there is no net energy change in the refrigerant. The refrigerant leaving the meter device has the same BTUs per pound as it does when it leaves the condenser. So flash gas. Flash gas is the vapor part of the saturated condition. So when you leave a metering device and you get expansion, you get flash gas occurring. Now, a lot of times we hear of flash gas as something that we don't want. If it occurs in a liquid line, it's really going to cause problems at the metering device. However, flash gas is just the ordinary outcome of any pressure drop that is equivalent to or greater than the subcooling of the refrigerant. So you'll see situations where this can occur in plugged components in a liquid line, but in the metering device, this is a necessity that we have to have in order for that refrigerant to drop in temperature. Why? Well, simple. Saturated R134A at 100 degrees contains 45 BTUs per pound. If you want to inject it at 20 degrees into the evaporator, well, saturated 100% liquid at 20 degrees only can contain 18 BTUs a pound. That means there's a difference of 27 BTUs per pound that you need to account for in order to have liquid or saturated liquid at 20 degrees. So where does the 27 BTUs per pound of excess energy go? It goes into making that flash gas. Now remember, vapor holds 5, 6, 7 times more energy than liquid does at the same temperature and pressure. So by that dropping the pressure around the liquid, it suddenly boils, it flashes very rapidly and forms this vapor. And that vapor is what holds that excessive energy. So if you want to know how much vapor you're going to produce in the previous example where we had 27 BTUs of excess energy, well, you're going to produce 27 BTUs worth of vapor, and the remaining liquid is going to be at saturation. Now, the liquid does all the work in the evaporator, going from a liquid to a vapor. The flash gas does very little. It's just along for the ride until the very end. All right. So if you can reduce flash gas by subcooling or pulling more heat on the high side, you can actually increase the amount of heat absorbed in the evaporator. So let's start with the most simple metering devices. Simple openings, orifices, pistons. All right, you'll see a lot of these. You'll even see them in the large centrifugal chillers. They look like a floor drain. These are very simple metering devices. They have a given size opening, and the amount of flow that goes through a given orifice, all else the same, is determined by the pressure drop. So across it. So if you have a given pressure between the high side and low side, that pressure differential will determine how much flow goes through it. And this is important because with pistons, as you'll see later on, the amount of flow and hence the amount of refrigerant in the evaporator, the amount of superheat and everything else is determined for a given set of conditions solely by the pressure difference across it. So with a cap tube, you size a cap tube for a given refrigerant and a given set of conditions, you size it for a given capacity. And the lower the operating temperature, the smaller the capacity, the longer you are going to have a given size of cap tube. So if you shorten a piece of cap tube, you'll end up with more flow through it and a higher evaporator pressure and temperature. So once again, cap tubes are cut to size based on evaporator capacity, temperature, and differential pressure. If you've ever done this, you'll have the box with the cap tubes in it, and on the back or in a sheet of paper or document, you will have the size of cap tube and the length you need to cut it for a given set of conditions. Now, cap tubes are a little different than pistons because you don't have that 100% relationship between pressure and difference and how much flow goes through it. And that is simply because cap tubes also have a friction element to it. Now, getting into this is beyond this presentation, but again, they just don't have that same simple pressure flow relationship like pistons. Speaking of which, if you look at this graph, it gives a clear indication of the superheat for a given load based on outdoor temperature. Now, your condenser's outside, right, in the weather. So as the temperature goes up, the pressure in the condenser goes up. Now, this forces more refrigerant into the evaporator, and that will drive down your superheat. And this is key because when you think about charging, when you think about proper airflow and keeping the condenser clean and free of obstructions and everything else, it comes down to this graph. If you artificially inflate the pressure or temperature in the condenser by 10 or 15 degrees, either by overcharging or poor airflow, you can easily get into a situation where you are going to flood the compressor. And this is a problem because a lot of compressors come back, even scrolls, with seized bearings smashed all up inside. And really, a lot of it comes down to this type of situation. So you've got a fixed metering device in your system. How do you tell if it's performing correctly? Well, straightforward, it's compared to the manufacturer's literature. So if you have an AC system, and we'll see in a second, it will tell you exactly how much superheat you should have for a given outdoor and indoor condition. In fact, this is what you use to charge a system. So if you're not familiar with this chart and you've been charging systems, something wonky is going on. So if your superheat is too high or too low for a given ambient condition, keep in mind you cannot modify or these are not adaptable controls. It's not like there's a knob on the side of a piston or a cap tube that you can turn that suddenly gives you less or more refrigerant like you can on a TXV. So it really comes down to what is going on in the system. Is the meter device sized properly? Is it plugged? All these kinds of things now come into play. So if your evaporator temperature is too low and your superheat is too high, then look upstream for any obstructions. You do this anyways, regardless of what the what's going on. If you have that low pressure, low superheat type or high superheat type of scenario, look for plugged filter dryers or plugged valves or whatever happens to be upstream. Also, if you have a cap tube, make sure itself is not plugged. So if you have, what looks like pure liquid entering into a cap tube, and you're getting very low flow on the other side, there's a good chance it is going to be plugged with wax or something like that. If your evaporator temperature is low and your superheat is low, make sure you have enough airflow and that your evaporator isn't iced up. And once again, check the piston capacity. If you have to pull it out, check to make sure you have the right one. If you have a piston that is too large, expect high evaporator temperatures, low superheat. In fact, you could probably expect flooding of the compressor on hot days. Once again, for cap tubes, a little more involved, check the diameter and the length and compare it to what the system is supposed to be. Believe it or not, when a cap tube is sized right and cut right, it feeds beautifully, especially on indoor applications where you have a relatively constant condensing. So here is a charging chart for a piston. You're going to charge it based on superheat. So on the left, you have your outdoor temperature. On the right, at the top, you're going to have your indoor wet bulb. Why wet bulb? Because this is AC. We don't have drastic changes in our indoor temperature. You might go from 75 to 73 or even 72 degrees, but really the majority of your heat removal is going to be in the form of latent or a big chunk of it if the system is operating properly, especially in the Northeast. So let's say it's 70 degrees outside and you're running your AC, right? The sun's out, you've got 64, 67 wet bulb inside. You're looking at 19, 24, 21 degrees of superheat. This is getting up there, right? Now, if it's wet inside and it's only 70 degrees outside and it's raining, you can look at maybe a 68 wet bulb inside. Now you're at 27 degrees of superheat. This is a problem because this pushes your average evaporator temperature up, which really kills your dehumidification. And this is a time when you really need it the most because you're really trying to remove moisture from the indoor environment because it keeps coming in. But if your AC system isn't working properly because you're not getting enough refrigerant into the system, that's a real killer. Now, during high ambient conditions, let's say it's 95 degrees outside, system will work great. If it's high wet bulb temperature inside, you're going to run 14 degrees of superheat. That's fantastic. You got a moisture removing machine. However, if it is hot outside, really hot, like 100 degrees or 105 degrees, and it's not wet inside, you don't have high humidity, now you're going to flood the compressor. So these systems have to be tailored for regional variances. If you live in a place where the air is very dry, you have to size a system differently, the piston, than what you would if you lived in, say, Atlanta or Alabama, where it's both hot and humid. All right. So once again, the biggest challenge with simple restrictions like pistons, okay, is if it's hot outside, or if it's cooler outside and it's not really hot, you don't have that high temperatures, you're going to have a hard time dehumidifying, all right, because your average coil temperature is going to increase. So if you look at an example here with a TXV, all right, your saturation temperature may be 43 degrees, you're running around 52 degrees average coil temperature. That was probably marginal for what you're looking for. Now you see a TXV on this system. Probably we made a mistake. It should be a piston in this image. However, suffice it to say, a TXV will solve a lot of your problems because they are an adaptable control. In other words, it doesn't matter if it's sensible or latent heat, you end up with a more capacity to match that load, which means you get lower superheat, lower average coil temperatures, and better dehumidification, like you can see in this picture here. All right. Again, I could spend a whole presentation on just this one area, and we don't have time. But one of the biggest selling points of an adaptable control like a TXV is simply when it comes to that dehumidification. Why? Well, here you go. Again, it's an adaptive control. It senses the heat load with the TXV based on the sensible temperature of the refrigerant leaving the evaporator. And the difference between that refrigerant temperature and the saturation temperature in the evaporator. The bigger the difference, the more superheat you have, right? The warmer that sensing bulb is going to be, and the valve is going to operate like the one on the right, where it strokes open, you're under high load, and the metering device injects more refrigerant into the evaporator. So even if it is cooler outside and your pressure differential drops, the TXV will still open up and put more refrigerant into the evaporator when you have a high latent load. So TXVs are very, very common nowadays in AC. All right. And of course, in refrigeration systems, larger refrigeration systems, they have been there for a long time. However, the AC front, residential AC, it really changed in 2007 when SEER 13 came in. It was during that period of time when efficiency increases were mandated in AC, and a lot of manufacturers went with TXV, and the entire market turned upside down, where the majority of meter devices going out switched from pistons to TXVs because they could get you a large chunk of the way there as far as necessary efficiency goes. So looking inside of one, this is a cutaway of one of our refrigeration TXVs. In fact, it's one designed for ice machines. And you'll notice that at the top, you have your diaphragm. You have a pressure plate in beige underneath it. And then you have your valve stem in green. The superheat spring surrounds that and is adjusted by the stem on the left. Near the middle there, the black, you'll see that's the orifice. So when the sensing bulb pressure increases, it causes the diaphragm red to be pushed down against the spring, pushing that orifice pin down in the middle, opening up the orifice and allowing more flow through here. In this case, the flow goes from left to right. If I reduce superheat, I reduce the force of that spring, allowing the valve to open up with less superheat. So there's two key things to remember here. Number one, the bulb pressure is the only opening force. The evaporator and spring pressure are both closing forces. So in order for the bulb to cause the TXV to open up, it has to overcome both spring and evaporator pressure. Now, that's why you don't have a TXV opening up at 0 degrees superheat, is because of the contribution of your spring pressure. So if the valve is rated for 7 degrees of static superheat from the factory, it means that you need at least 7 degrees of superheat for the bulb pressure to be high enough to overcome that spring pressure. So when you adjust the superheat on a TXV, you are really increasing or decreasing the contribution that that spring puts in. Next important point here is internal, external equalized TXVs. I see a lot of questions, a lot of discussion on this. A lot of people don't seem to understand the underlying reasons why you may need an external equalized TXV. Well, it's pretty straightforward. It has to all do to the pressure drop that occurs between the TXV outlet, the inlet of the evaporator, and where the sensing bulb is located at the outlet of the evaporator. If you have a small pressure drop, equivalent to a couple of degrees, let's say, the TXV, internally equalized, will work just fine. However, if you have a multi-circuited evaporator, one that has multiple circuits to allow for a more even evaporator face temperature, then you have to use a distributor. And refrigerant distributors are notorious for having very high pressure drop, anywhere from 5 to 30 pounds. Now, here's the rub. Whatever temperature equivalent that pressure drop is equal to, you're going to have to add to the superheat setting of the TXV, because the TXV doesn't know there's a pressure drop downstream of it if it's internally equalized. So it thinks the evaporator temperature, saturation temperature, is much higher than it really is. It might think it's 40 degrees when actual fact is 25. So whatever temperature difference that pressure equivalent is equal to, you would add to the opening superheat, static superheat. So if you had a 10-degree equivalent pressure drop and the static superheat on the valve from the factory was 7 degrees, 10 plus 7 is 17. Your valve would not even open up until you had 17 degrees of superheat. You would always underfeed the evaporator, and it would be a disaster. So by going with an external equalized valve and attaching the external equalized valve just downstream of the sensing bulb, you get the actual saturation pressure where the sensing bulb is located, applied under the diaphragm, so that you have like for like forces on that diaphragm. So here we have two TXVs. Both of these are TUAEs. The one on the left is internal equalized. You can see the opening here in this area right here that allows the evaporator pressure up and under the diaphragm. The one on the right, it's closed off, but we have an opening on the side. So we cannot let the evaporator pressure here up there. We take it from the outlet of the evaporator after all the pressure drops and apply it up under that diaphragm. So once again, you get a much more accurate picture of what the conditions are inside the pipe where the sensing bulb is. So the rule is you can use an external equalized TXV even if you don't need one. You still have to connect the external equalization line. Keep that in mind. However, you can never use an internal equalized one if you require an external equalized TXV. If you have a distributor, you absolutely should have an external equalized TXV. That's why you'll always see external equalized TXVs on air conditioning systems. So, superheat and load. Now, different manufacturers take different approaches to this based on what mixture they put in the bulb charge, and we'll talk about bulb charges in a second. However, in order for you to compress that superheat spring, the more you push down, the harder it pushes back up again. So you need more bulb force to continue opening that TXV. So to drive it wide open takes much higher bulb pressure. Now, you can increase some of that bulb pressure just by having a different mixture. However, you're always going to have an increase in superheat under high load. It's not going to be as much as you would with a piston or a cap tube or whatever, but there is going to be some. It might be 4 or 5 degrees of superheat difference between closed and your rated capacity. And we call this opening superheat. When you measure superheat leaving the evaporator, you're measuring operating superheat. And that is both your opening and static superheat combined. So if somebody says, I've got 12 degrees of superheat at the evaporator outlet and your static superheat is 7, you have 5 degrees of opening. And every TXV has a certain amount of superheat to drive it to its rated capacity. However, all TXVs that I've ever ran across has what's called reserve capacity or extra capacity. It might be 20, 30, 40% above what it's rated for. Why we don't rate it for a 1.4 ton valve instead of 1 ton? Well, because that is really not a place we want that valve to be running all the time, because it doesn't have that same accuracy as far as amount of opening compared to a given amount of superheat. It is far more accurate in this area down here. And this is really where we want to operate most of the time. If you're in pull down mode, it's okay to be up here for a short period of time until you get that load pulled down, but you don't want it operating up there all the time. So once again, your superheat is reflective of your load. Some manufacturers will have less change, some will have more, but either one will have, all of them will have some. Okay, now the important part. In order for you to understand if a TXV is working correctly, you have to understand what it does under different conditions. So you can tell if there is something wrong with the valve itself, or if there is something wrong in the rest of the system. So you have to know what the TXV is going to do, what you expect. Because if you don't, how are you going to know if it's operating properly or not? It's pretty straightforward. On the left, you have a coil. Coil's well loaded. It's in a cooler. You're running around 24 degrees. You might have a 36-degree box temperature, and you've got 12 degrees of superheat, lots. On the bottom, you measure the liquid temperature leaving the condenser. You've got 10 degrees of subcooling. On the right, you have an issue here. You have low load. Now, there's several things that cause this: icing, dirty air filters, failed fan motor on the wrong speed, or you could have an incredibly wide differential on the thermostat that just lets the system run, even though there's no load. Either way you look at it, you're going to pull that coil temperature down. So you're running around a 5-degree evaporator temperature. However, this is not a problem with the TXV. The TXV has done exactly what it's designed to do. There's no load. You don't want to flood the compressor, so it throttles closed. And when it throttles closed and injects less refrigerant into the evaporator, the compressor is going to pull that evaporator pressure down, because that's the only way it can balance the pumping capacity of the compressor. So look, you got a 5-degree evaporator temperature. Now, don't start monkeying around with the superheat or dumping 50 pounds of refrigerant in the system until you look at a couple different parameters. Number one, your superheat. Your superheat is very low. It's only a couple of degrees above the static superheat of the TXV, right? This means that the valve is fine. If you had too low of a superheat setting on a TXV, it means it would be dumping more refrigerant into the evaporator. So your evaporator pressure wouldn't go down, it would go up. So the fact that you have a low evaporator temperature, low superheat, means it is an airflow problem, not a refrigerant problem or TXV problem. It is also not a charge problem. You don't get low superheat by being undercharged. If you want to verify that, look at your condenser subcooling. You got 7 degrees of subcooling. It's a little bit lower, but you have a solid column of liquid in your liquid line. So there's no point in adding refrigerant. It is not going to correct this. So before you add refrigerant, check all 3 of these parameters. Before you adjust superheat, check the 2 parameters, evaporator temperature and superheat, and verify them before you make adjustments. Because if you go making adjustments or adding refrigerant, and that's not the problem, now you've just added more issues to deal with. And the more unknowns you have, the harder it is to solve a problem. So let's look at the next part, that mystery material that's inside of the sensing bulb. Now, a lot of people think, oh, it's got the refrigerant in there. It's an R404A system, it's got 404A refrigerant in there. No, it does not. These have not been charged with straight refrigerant since, I don't know, friggin' Carrier was alive. It is a mixture of different gases or different chemicals depending on what you want to do. Yes, it probably will have R404A in there, but it will also have a bunch of other stuff like nitrogen and some hydrocarbons, or who knows what it's going to have in there. But really, what you want to do here is you want to have this work over a wide temperature range. In order to do that, you're going to have some of the material, some of the liquid in there boil off quicker and some boil off slower. so that you can tailor how that valve reacts to a change in load. Now, the wider the operating temperature you want to work at, right, without having to change bulb charges, the more complex the bulb charge has to be. So with our end charge, we work from -40 to +50. It's great. But we also have a multitude of different materials in that charge. It's not just straight refrigerant. So the question is, why would you not want to put straight refrigerant in there? It's very straightforward, because the amount of pressure required to change the temperature a certain amount, or vice versa, the amount of temperature change that's required to change the pressure is not constant in refrigerants. In other words, the amount of pressure change for a given temperature change is much smaller at low temperature than it is at higher temperature. So if you look at the chart here, we're going from 15.7 to 19.6. That's 3.6 psi to give you a 5-degree temperature change. Whereas on the right, it requires a 17-pound difference to give you a 5-degree temperature change. So even if we don't go to that extreme, you can still see what the problem is going to be. And it comes down to this, the superheat spring. The superheat spring applies the same amount of force, whether you're running at -40 or +50. It doesn't know the refrigerant temperature. All it does is push back a certain amount. Now, nominal ratings for a TXV are done at 40 degrees Fahrenheit. So if we say this spring force is equivalent to 7 degrees of superheat, that is at 40 degrees. So if we look at a 7-degree change at 40 degrees, that is 12 psi. In other words, this spring pressure always pushes with 12 psi of force. All right, so what's that mean? Well, if you're going to run this thing at -20, all right, and you want to overcome 12 psi of force, look how much superheat you're going to have. It's not going to be 7 degrees at -20. It's going to be a lot more than that, because 5 degrees is only 3.6 psi change. So how are you going to get 12 degrees? Well, in this case, you're going to have to bump that superheat all the way from -20 to, or the temperature from -20 to -6 before you get 12 psig. This means you're not going to open that valve unless you have 14 degrees of superheat. So you will find that your opening superheat goes up at low temperatures if you were just to use a standard refrigerant, and vice versa. At high temperature, you would overcome that spring pressure with very little superheat, possibly causing the evaporator to be unstable. That's why we always use a mixture. Okay, so how do you know if the TXV is operating correctly? Well, that previous example that you saw where we had a drop in load and a drop in evaporator temperature, a drop in superheat, and stable subcooling, I gave that as an example of something that's not a metering device problem. There is no change that you can make at this point that is going to improve that situation that is beneficial. So it's either going to be an airflow change or a defrosting situation or something else that needs to be addressed. So always make sure you check airflow. Make sure that you have the correct airflow for the situation. Otherwise, if you don't have correct airflow, none of this other stuff matters. There's nothing you can do that's going to improve it, because you're not going to have the load that the system was designed to have. So check what your airflow is. It's going to be over a range, but you can compare it to what the manufacturer wants, or you can look at the system. If it's a block of ice, there's something wrong. Okay, so generally speaking, superheat and evaporator pressure tells you basically how much refrigerant you're boiling, and low evaporator temperature tells you you ain't boiling too much, and low superheat tells you you got lots of refrigerant for the load. So that tells you right then and there you have an air side issue. All right, so if superheat is too high, and it should be, and evaporator pressure is too low, check TXV orifice capacity at the actual evaporator temperature. Now, for AC, this is not a big deal. because it's 45, 43, 46 degrees, right? TXV is going to work great. If you got a nominal 1 ton TXV, you're going to get 1 ton and a little bit more at 45 degrees. However, if this is an ice cream freezer and you're running your evaporator at minus 20, well, that 1 ton TXV nominal capacity is only going to give you a half a ton. So you need to size the TXV based on your unit cooler, your evaporator capacity, at the temperatures designed to operate at. Minus 20, minus 10, plus 20, whatever it happens to be, and make sure that that TXV, the orifice that you have inside of there, is going to match that unit cooler evaporator capacity. All right. Why do I say that's number one? Because you will be surprised how many times it's not. And you can waste a whole lot of time dorking around and doing stuff when really you could have solved the problem in a few seconds by just verifying the capacity of the TXV. All right. Number two, check for subcooling at the condenser outlet. The reason I say this is because there seems to be this trend of wanting to add more refrigerant. And listen, over half the systems out there are overcharged to the point where it's causing issues and failures. So adding more refrigerant is probably not going to solve a problem unless it's absolutely necessary. And even then, you got to figure out where the refrigerant went, right? Before you just start adding more. So check subcooling at the condenser outlet. If you've got subcooling, especially according to a charging chart, or if you've got 6 or 7 degrees of subcooling and it's fairly warm outside with a good load, you are okay. If you don't have flash gas at your metering device, right, from the condenser all the way to the TXV, you do not need refrigerant. All right. Very, 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 very rare that you would. Next thing, check for upstream obstructions. If you've got a partially closed ball valve because somebody forgot to open it, you've got a stuck solenoid valve, you've got a plug filter dryer that's frosted up on one end or sweating and has a high pressure drop, that's going to cause flash gas. And if you have flash gas at your metering device, you're trying to force vapor through a little tiny opening. That's going to be a problem. So you're going to end up with a low evaporator temperature and high superheat because you don't have enough refrigerant for the load. So make sure you do these checks before you do anything else. Trust me on this one. I've been burned myself with this. So it's a very quick check. You got your hands, your eyes, and your ears will tell you a whole lot about this, okay? Without ever having to take out a tool other than maybe a thermocouple to take a measurement. All right. So a low evaporator pressure must be accompanied by high superheat to indicate a lack of refrigerant in the evaporator. If you have low evaporator temperature and low superheat, that is a load issue, and you must treat it and solve the problem as a load issue. If pressure and superheat are low, once again, check your airflow. Check to see what is going on. All right. If everything else is okay and you don't see any other issues, you've eliminated all these other possible problems, you can adjust superheat. Remember, when you adjust superheat, the valve will react instantaneously. In other words, if you reduce superheat, the valve will immediately inject more refrigerant into the evaporator, and your evaporator temperature will go up and your superheat will go down, and vice versa. The reason we tell you to wait 10 minutes is for the system to stabilize, and this is very important. However, if you're determining if the TXV is functional or not, as soon as you put a couple of turns in, if you see no response, something is wrong with the valve. All right. So, or something's wrong inside the valve, I should say. So hold the sensing bulb in your hand and warm it up. Don't put a torch on it. Don't put it in boiling water, anything stupid. Just hold it in your hand and warm it up. If you see a response, all right, this tells you then that the valve was probably stuck and the larger pressure differential was enough to overcome any issues. All right. However, if there is no response, then one of two things is the valve is really plugged or you've lost your bulb charge. It doesn't matter. The valve's got to come out. All right. Well, before you condemn the TXV, take a look at the inlet, the liquid inlet. You'll see a screen there. It may be removable, like in the TUA, or it may not be. But even if it's not removable, if you see it's plugged up, that tells you the reason for the failure. The recommendation then, of course, is to replace the TXV, replace the filter dryer, and wonder why it didn't catch the problem, right? And I would recommend flushing the system because you've obviously got crap in there that's going to cause a problem. All right, that's my recommendation on what to do. All right. Okay, finally, we're going to deal with electronic expansion valves. Now, just like TXVs made an entranceway into lower end systems, electronic expansion valves are now making their way in. Just like anti-lock brakes, right? The first vehicle to have anti-lock brakes was the Concorde. The second one was probably some $500,000 car somewhere. Now you can buy them on your, Hyundai, whatever the thing is, right? They come with anti-lock brakes. So electronic expansion valves are adaptable meter devices that basically utilize a pressure and temperature input to a controller. And the controller uses that information to determine superheat. And based on a set of algorithms, it will either open or close the EEV, electronic expansion valve, based on that value. Now, the main thing that determines how much flow goes through a given electronic expansion valve is the pressure difference across it. Remember, electronic expansion valves, when they say 5 tons, they mean 5 tons. There isn't 20, 30, 40% reserve capacity like there is in a TXV. So if your TXV has been operating using that excessive capacity and you replace it with a EEV of the same nominal capacity, you're going to be in trouble because it doesn't have that surplus capacity. Now, notice something here. If you were to size a TXV, you would notice a huge difference at a given condensing temperature between -40 and +55, right? With electronic expansion valves, you don't see that. It is based solely on the pressure differential, and they will give you gobs of capacity at -40, and they will give you gobs of capacity at 45 degrees. It all depends on the pressure differential. And the nice thing is you can tailor how they open, right, in your controller. So you can see that you can set these up to open up slow at low load to allow fine control, and the thing can ramp up quickly at high load to really match load change. So the one type that we have of 2 is pulsed with modulated. This is like a high quality, long life solenoid valve. It's either open or it's closed. And the benefit is if it's open, it's 100% open. It creates nice turbulent flow, good oil return, on and on and on. There have been some changes to them to make them less prone to hammering and noise, and that's been a big advantage. However, being an on or off control and nothing in the middle, it is either on or off. And how long it stays open determines how much capacity you have. And so for Danfoss uses 6-second intervals. If you want 50% capacity, you're open for 3 of the 6 seconds. If you want 100% capacity, you're open for 6 of the 6 seconds. So the valve is constantly opening and closing. And if you know what a solenoid valve looks like inside, you'll recognize this. There's your valve seat, your orifice, and your plunger. You energize that coil, the plunger will lift up and separate and center itself in the magnetic field, moving away from the orifice and allowing flow to go through. De-energize the coil, and the spring in the middle of the plunger will push it back down into the closed position. The other type of electronic expansion valve is the stepper motor, and the stepper motor has an actual motor. And the motor turns in one direction or another depending on the polarity that you send to it. And in doing so, it turns a threaded rod in the middle that either threads down or up. And attached to that is a needle valve. Thread it down and the needle valve closes against the seat. Thread it up and it opens. So these operate over a set of steps. And whether it's opening or closing, once again, depends on the polarity. So you might have these things with anything from 50 steps between full open and full close to like 600 steps between full open and full close. And you can select that to basically control how slowly or quickly the valve opens up and how accurate it can be. So the motor works off an opposite charge attracts a principle. So you can see the outer magnet and the permanent inside magnet. So whenever you move that north pole around, the south pole of the inner magnet's going to be attracted to it and it's going to turn towards it. And so you can literally step this thing around in a circle by changing the polarity of the outside magnet. And to make it go the opposite direction, you just reverse the polarity of the outside magnets and it starts to push it in the opposite direction, closing the valve. So let's leave with this here. Minimum stable superheat. A lot of people don't understand why a TXV starts to hunt if you reduce superheat too much, and why it would only hunt during certain periods. Well, the reason is this. When the evaporator tube has lots of liquid in it, it's not a problem. There's enough weight there to hold it all down, and the vapor stays on top. But as soon as the liquid fraction drops below a certain amount, there's enough vapor to start lifting the liquid up away from the wall. And you can literally have vapor that's superheated 2, 3, 4 degrees against the pipe with liquid floating in the middle. And of course, that mixes. It's not uniform or laminar. So you will replace that superheated vapor with liquid and go from 3 to 0 degrees of superheat. This drives TXVs nuts because they're trying to determine the superheat. So what do? They open and close. So the minimum stable superheat is the amount of superheat for a given evaporator that guarantees you no mixing and dry vapor at the outlet. And it is a curve, and each evaporator has a slightly different curve. So you can see that the minimum stable superheat is lower at low load compared to high load, but it's a unique fingerprint for each evaporator. Now compare that to a TXV, which is linear, and you're putting a straight line against a circle or a curve. It's only going to touch in one place. Where it doesn't touch, the TXV demands higher superheat than what the evaporator needs. If you try and adjust your superheat too low, you put your TXV down into the unstable area and it doesn't work. If you put it too high, it's going to be stable, but now you're having too high of a superheat. What an electronic expansion valve does is it's always trying to reduce superheat as low as possible. So it pushes it down, down, down until it starts to become unstable. Then it increases it a bit. So it's always hugging that minimum stable superheat curve, always allowing you to have or guaranteeing you the lowest possible superheat. This allows you to operate your evaporator temperature a little bit higher, which means it lowers your compression ratio and saves you energy. It also gives you great dehumidification. So that's it. You have seen the difference between fixed and adaptive devices and how to really tell if they're working correctly or not. I wish I had more time, but unfortunately, we're out of time. Thank you for joining us today.
All right, thank you, Jamie. Let's open things up to some questions. Appreciate everyone who submitted one.
Cool, let's have them.
All right. First question is, what happens if we use the wrong orifice in expansion valves?
Okay, one of two things. If it's too small, the TXV is going to continue to try and open. So what will happen is you'll be up inside of that reserve capacity. So if the load on the system isn't very high, you may get away with it. You'll just see a couple degrees higher superheat than what you should have. However, if you were to load that cooler and freezer up and try and freeze or cool whatever you put in there, now you're going to have a problem because the TXV can't give you enough capacity to do that. So instead of taking an hour to cool something down, it might take 2 or 3 or may never cool it down, right? Especially in a kitchen or something like that where the door's always being open and closed. The opposite of that is oversized. Now, with a TXV, oversizing it doesn't really have as much of a negative result as undersizing it does. And the reason I say this is because if you mount the sensing bulb correctly, right, where there's no oil, right, you make sure it's well insulated and as tight as heck, and you've got a metallic bulb strap that's holding it tight against the pipe, right, and there's no external heat factors on the TXV or on the bulb, you're probably going to be okay, because just about any TXV is going to modulate down to around 60 or 50 or even 40%, no problem. The only time you might have an issue is if your system has a very wide capacity range. And if you like to operate that system down around 30%, and your TXV is 50% or twice as big as it should be, now you're going to have a problem. Because if the TXV is not stable, if it overshoots or undershoots, if it's got more capacity, it's just going to do that much more. So really, the big issue here is, obviously you want to select the TXV, but I see probably 90% of the issues with TXVs that I've run across is when they're too small, capacity-wise. I hope this answers your question.
Okay. Next question. How much pressure is there in the bulb? Which gas is there inside the thermal bulb?
Well, good question. I really don't know, because that is up to the guys at the lab who determine the mixture that goes in there. Now, keep in mind, we've got mixtures for low temp freezers. We've got mixtures for air conditioning. We have what's called an MOP charge, so does everybody else, maximum operating pressure charge, that makes sure you run out of liquid so that you can't raise the bulb pressure any higher past a certain point. The reason they do that is because you don't want the TXV to open up too much on a low temperature system. Because if you're coming out of defrost and your compressor can only operate to 15 degrees Fahrenheit, you're coming off a defrost at 40 degrees, you don't want to overload that compressor. So the sensing bulb will not generate enough pressure to overcome that high evaporator pressure. What happens? You don't inject refrigerant into the evaporator at the start, and the compressor can easily get that evaporator pumped down. We also have an anti-hunt charge, which causes it to react very slowly to changes in load. We have charges that basically are designed for ice machines. They allow a very wide temperature swing and minimal superheat without flooding the compressor. So to answer you, I really don't have an answer, except to suffice to say, the wider the operating temperature, the more things you want that bulb charge to do determines how much more complex the mixture is going to be. And how much charge you put in there is also determined by the pressure range. If you want it to operate across a very wide pressure range, you need lots of stuff in there to boil off, right? If you don't want to operate at high pressure, in the case of a maximum operating pressure situation, you reduce the amount of charge so that you basically run out of horsepower at a given evaporator pressure, and the valve will not open up anymore. So to answer to your question is basically application dependent.
Okay. In 1.5 to 5 ton systems, how important is the placement of the sensing bulb as it relates to the equalizer connection?
Good question. I was taught by the guy that mentored me when I first got on the tools that the sensing bulb should always be upstream of the external equalizing line. And what he told me made sense to me. He said, if you get a leak through the valve, up past the valve stem, it will generally go straight out the external equalizing line. Now, if the sensing bulb is downstream and close to the external equalize line, and you're metering refrigerant directly into that vapor area, you're going to change the immediate temperature of that area. And this is going to affect the sensing bulb, cooling it down and causing it to throttle closed. And you can get in a hunting situation. It's not going to harm the compressor per se, because you're not dumping liquid in there by the gobs of it, but it's enough to possibly influence the sensing bulb. Now, keep in mind, this guy was probably referring to 1970s technology, and who knows, maybe sensing bulbs or maybe TXVs are far less prone to leak nowadays. I have no idea. I've certainly seen enough of them myself leak when we get them back on warranty. Usually they have the crap burned out of them. But suffice it to say, that's what was told. I was told. I have verified it with several other techs that do the same thing. However, you will see manufacturers actually place the sensing bulb downstream of the equalizer line, usually because they don't have room to put it upstream. So they are forced to put it downstream. But that's really all I have to say at it. In my view, upstream is better. If you have no other choice, put it downstream because you have no other choice. Simple as that.
Okay. Can you change a fixed orifice metering device to a TXV?
Yes, absolutely. We have a TR6 kit that is basically a Danfoss TR6 with adjustable superheat, the same as they put in the OEM units. And you can buy them from 1.5 to 5 tons, and they come with a chat-lift chat-lift or air-equip, air-equip, and flare connectors to match on to the distributor. And the main thing you got to do 100% is you have to make sure that you leave that job site with that orifice in your pocket. That's what I do. Because if you leave that orifice in there, the TXV will still happily stick on there, and you'll end up with both an orifice and a TXV in series, and it will not work better, trust me. So you remove that orifice, you put an equivalent capacity TXV in there, and you will notice about 20 or 30% energy savings and much better dehumidification. A big chunk of the energy savings, almost half of it, comes from the valve closing shut tight during the off cycle and not allowing the pressures to equalize. So the system is not wasting energy trying to rebuild that pressure differential, waste energy, and really not giving you effective cooling for a specific amount of time. And the more often the system cycles, the more often that's going to happen. Keep in mind, if you've got a piston compressor, a recip compressor, you're going to need a start capacitor on there, right? And a relay, because it will not have enough starting torque to overcome that pressure differential. So the answer is yes, absolutely, highly recommended. If you have the system open already, change that piston out, put a TXV. Good question.
Okay, well, that's all the time we have for the questions. So if we did not get to your question today, Jamie will be answering the rest of the questions on our Twitter page at Danfoss-KOOL US. So just want to thank you, Jamie, and again, thank you everyone for attending today's webinar. As you can see on the screen, we encourage you to connect with both Jamie and Danfoss for more e-learning opportunities, videos, tips, tricks, and tools. Jamie will be hosting 2 more webinars over the next few weeks.
We got a couple more to go.
So please visit danfoss.us and scroll down to the latest news to sign up for those as well. For recordings of today's and past webinars, please visit our YouTube channel, Danfoss-KOOL US. And once again, thank you everybody and have a great day.
Thank you. I appreciate it.